Okay, chapter 3. It is kinematics in 2 dimensions now. Previous chapter was 1 dimension. Now we have to work out uh, 2 dimensions at once. And of course, for doing that, we need to understand how vectors work. The vector algebra is the main focus because it turns out that any vector will follow those rules that we're going to discuss. And once you're going to multiply 2 vectors, one vector by the other one, you have 2 options as a dot product or cross product. And for now, we're not going to do any of that. Let's just focus on how you add, subtract vectors, and multiply vector by scalar. So this is a short introduction on what we're going to do. So vectors and scalars. We already know that we have 2 types of quantities. The first one is a scalar, when it's just the magnitude, just the value, just the number, and some units next to it. And there's no direction that you can possibly assign to that value. Say, for instance, time. You can say time goes due east, right? Or time goes backwards. So for time, it's just the amount of seconds, and that's it, no direction. And then we have displacement, velocity, acceleration, forces, momentum, torques, plenty of quantities that will involve both magnitude and direction. You have to specify direction. You have to draw a sketch and specify the direction for a certain vector. So, for instance, a displacement vector, my particle moves from point A to point B, and that's the vector that shows that you start at A and you draw an arrow towards point B. That's it. Easy as that. The amount of units in this vector tells you the magnitude. So the longer the arrow, the more the magnitude. And direction is clearly shown. This time it's what? North of east, right? So there are many different ways to specify direction. I suggest you always draw a sketch and show some kind of a reference angle and tell me the value for the angle. The angle can be any value from 0 to 360, and the angle speaks for itself. Just make sure you show the reference angle. Is it with respect to the horizontal axis? Is it with respect to a vertical axis? You have to choose your reference frame and specify the direction with respect to that frame. Say, you know how there is an angle of 90 degrees, and you can say, oh, this angle is 30, so the other one is 60, and my answer might be 30 degrees, but your answer might be 60 degrees. And if you show the proper angle on your sketch, I'll give you full credit because it's either 30 here or 60 on the other side. So I can't say that 30 is better than 60. I can only say it's better if you choose the same angle that I call 30 and you will call it 60. Then we have a problem. Then you don't know which angle we're talking about. So make sure you specify direction with respect to a certain axis, x-axis or y-axis, positive, negative direction. So be careful with that. And 2 vectors are equal to each other, or you say identical, if and only if they have the same direction and the same magnitude. If magnitude is not the same, they're not equal. Let's say magnitude is the same, but direction is not the same. Well, they're not identical as well. If one goes A to B and the other one goes B to A, they're not equal. They would be opposites of each other. So how do you add two vectors? First of all, let's do in single dimension because we already practiced the adding vectors in one dimension, so there should be no surprises here. And then we'll go to two-dimensional vector algebra. So here we go. The first displacement is 8 kilometers due east. Yeah, I know kilometers not the best units. Well, it is what it is with the diagram. Consider just 8 units in a certain direction. And then you have another vector, another, say, displacement of 6 units, also due east. What would be the result of adding those two vectors? Well, you say, hey, tip to tail, you go all the way to 8, then you go 6 more, and the result should be 14, and the direction is due east. Let's take a look at the bottom example. You go 8 kilometers due east, and then you go 6 kilometers backwards, due west. Then where are you now? Well, you will be at 2 units position. So the total displacement from initial to the final point, it's only 2 units, and it's still due east. So I want to point out that the way you do it is always tip to tail. So you draw the first vector, and then from the end of the first one, you put the beginning of the second one, and then as a result, you connect the initial position from the first one and the final position from the second one. So be careful about the signs because 6 kilometers can be backwards, and with that, you will get a -6. If your positive direction is due east and you're going due west, then it's not +6, it's -6 for your calculations. Now, this is the general rule. I've already mentioned that you have the first vector A, and then you have the second vector to add to A, which is B. And the first method to do so is called triangular method, and I'm pretty sure you can see why it's called triangular method, because you see it as a triangle as a result. And the rule is simple. You draw the first vector, and tip to tail, from the end of the first one, you start drawing the second one. And then for the sum of two vectors, you connect the beginning of the first and the end of the second. So vector S is the vector sum. Compare this to the parallelogram method. Why is it called parallelogram? Well, you can see that the final result is indeed a parallelogram. And your vector sum is now the diagonal of the parallelogram. And remember that each parallelogram has 2 diagonals. So which one is it? It's easy to remember because you can see how in triangular method, it's tip to tail. So the end of the first is the start of the second. Now in the parallelogram method, all vectors start from the same point. And most of the time, you will probably choose this way of adding stuff because it's just convenient, and you're used to say x-axis, y-axis, and you want to add the 2 components, and boom, you have the result of that vector addition. So consider parallelogram method as your primary way of solving like 90% of the problems. And still, you want to keep in mind the triangular method just for the general reference. So once again, all vectors in the parallelogram method start from the same point. Okay, vector A goes one way, vector B goes the other way, and it's the diagonal that is the sum. It also starts from the same point. Do not pick the other diagonal. The other diagonal is an incorrect choice. So you have to work with the same point. and you draw that diagonal. And if you'll take a closer look, you'll see that the way we add two vectors here gives you the same result that we add vectors there. Remember that for parallelogram, opposite sides are parallel and equal. So this vector A corresponds to this vector A. This vector B corresponds to that vector B. And once you complete the parallelogram from the initial setup of A and B, you'll be able to draw the diagonal that is the sum, which is the result for the adding two vectors. We'll practice that and you'll see how this works. Good news, it doesn't matter whether you want to go A plus B or B plus A. So you can go A plus B, and this is your diagonal. Or you can go B plus A and still get the same diagonal. So this is what we call a commutative law. So for vector addition, you can flip-flop things around. Be careful, you cannot do that for subtraction, because A minus B is not the same as B minus A. You have 3 plus 5, it's the same as 5 plus 3, right? But if it's 5 minus 3, it's not the same as 3 minus 5. 5 minus 3 is 2, and 3 minus 5 is negative 2. So be careful with commutative law. It is only good for vector addition, not subtraction. So here is some practice on how you add two vectors, say two velocity vectors, v1 and v2. You start with v1, and tip to tail to tip, you draw the v2. So this is your v2. This is your v2 on the triangular method. And you connect the beginning of the first and the end of the second. Boom, this is the result. This is your triangular method. Should be clear and straightforward. Now for parallelogram, once again, you start from the same point. Everything starts with the same point. V1, V2, and what's even more important, the result is also from the same point. You cannot pick the other diagonal. See, it says incorrect. Either way, this way or the opposite way, you're going to get the incorrect result. So that's what you do. Let me know if you have questions. And we move on to subtraction. For subtraction, it's easy to understand if you understand what subtraction is in the first place. Consider 5 minus 3, right? 5 minus 3, everyone knows it's 2. So what do you do here? What you do here is actually you're still doing subtraction, you're still doing addition. But your second term is negative. So it's like 5 plus minus 3. Okay? You can replace subtraction with addition because plus and a minus gives you the minus. So instead of thinking as 5 minus 3, think as 5 plus minus 3. You still get 2. And instead of doing subtraction, you're actually doing addition. It's just you're adding the opposite. And what does it mean to add the opposite? What kind of opposite vector are we talking about? Well, that's the diagram that shows you what's going on. If vector v, say velocity vector, is what, north of east, then the opposite is south of west. So instead of subtracting v, you can add the negative v. And adding vectors, we already know. Let's go back. You have two options for that. You can do triangular method or parallelogram method. Either way, you should get a good result. So let's practice that. Two vectors, v2 minus v1. And instead of minus v1, I want to add the opposite. So I say v2, as before, my first vector v2. And then instead of subtracting this vector, I want to add the opposite of the v1. And see how it was due east? The original one was due east. Now, for subtraction, you're doing the opposite. What's opposite for east? Opposite is west. And that's exactly what you have here. Magnitude is the same. If it's 5 units here, you have to draw 5-unit vector in the opposite direction there. And you finally get the addition. So you start with v2. That's your v2. And the negative v1, that's due west. And you do the triangular method. And that's the vector sum. But this time it's a sum with a negative vector. The second vector is negative. So essentially it's plus minus v1, which is subtraction. That's the result for subtraction of two vectors. So instead of doing subtraction, add the opposite. That's how you do it. Now, one last operation with vectors for this chapter is multiplying a vector by a scalar. Scalar is just a number, no direction. But scalars can be of two types. Can be positive or negative. And if this is your original vector, v, and you want to multiply this by, say, positive 1.5. First of all, you should notice that the value increases. It was like 1 unit. Now it's 1 unit here and half of the original added on top of that. So you have a larger magnitude, longer distance, if you will, to show the vector. But what's good about it, it has exactly the same direction. So if you multiply or divide, because division is still multiplication by the reciprocal, you will still get the same direction. Direction does not change. And the second example, you want to multiply by a negative or divide by a negative, because once again, division is still multiplication by the reciprocal. And once again, you get larger magnitude. In fact, it should be exactly double of the original one. If the original is this many units, then the final should be double in terms of length. And what's even more important, direction changes exactly to be the opposite. So it was once again what? North of east. Now it's south of west. Okay, and with that brief introduction to vector algebra, we go straight to the actual physics that you're going to do. And it's not just for velocity vectors that you see here. Everywhere you see vectors, you have to do this method. It's called adding by components. So you're going to decompose a vector into components and treat them as separate problems. Add all the x components, then add all the y components, and then do the distance formula from the Pythagorean theorem, which we'll discuss later. For now, what you see here is just a random vector, velocity vector. And there is a reference angle. Remember, I said you should always show the reference angle. This time it's reference with respect to horizontal axis. And the angle is 30 degrees. So your first task is to decompose this vector into components. Specifically, figure out how many units are there in v sub y and how many units are there in v sub x. And this time they're both positive because this is your positive direction for x, this is your positive direction for y, so both components will turn out to be positive. It's not always the case, because if your vector, say, points in the second quadrant, for a second quadrant, you will get a negative x component. positive y, but negative x. If your vector is pointing in the third quadrant, then what? Well, then you'll get a negative x component and negative y component, because both components would be pointing against your positive direction for motion. And for the fourth quadrant, if the vector points in the fourth quadrant, then what? X is positive, but y is negative. So your positive and negative, you have to keep in mind, you have to keep track of that, because once you start adding those components, if you're adding a negative, you essentially subtracting. So be careful with your sign for components. This time it's both positive because vector v points in the first quadrant, into the first quadrant. Excuse me. So this was parallelogram method, as you can see. This time it is triangular method, and your v is still a vector sum of x and y components. And in here, it's easy to see that once you want to calculate the components, you are pretty much talking about a right triangle. And in that right triangle, you know one of the angles. And let's say you know the actual hypotenuse value, say, I don't know, 10 units. Then basic trig allows you to calculate the x component right away and y component right away. The x component comes from multiplication of the hypotenuse by the cosine of angle. Cosine represents the adjacent side. And opposite side is for the sine function. So your v sub y component for that vector is multiplication between the hypotenuse and the sine of that angle. Let's say you don't know the hypotenuse, you want to solve for hypotenuse, but you know both components, which actually is going to be a very common scenario for this class. You'll figure out the components, and then your final task is to specify the original vector. And for that, you have to do the Pythagorean theorem or the distance formula, whatever you call it. It doesn't matter, it's pretty much the same thing. It's the first side squared plus the second side squared, and then the radical out of that will give you the magnitude for the original vector. I want to stress out the word magnitude. For the vector, you have to show two things. Remember, it's not just the magnitude, it's also direction. So for any kind of problem, once you're asked about a certain vector quantity, do not forget to specify the reference angle. It's not necessarily this angle, it can be the other angle. And you have to make your choice and specify which one is your reference angle so that I can grade your paper properly. You have to remember what the sine, cosine, and tangent functions are. Well, I'm not going to give it to you for the test, and life is not going to give you those definitions as well. So make sure you remember the basic trig and the Pythagorean theorem. If you have trouble understanding what's in this diagram and what you do, you really have to go back to trig class and go through those definitions once again. So see how drawing a diagram is essential. You really have to show your reference angles, your components. Positive, negative values are kept only with respect to a certain reference frame. So X and Y coordinate system is a must. You can always cheat a little bit and try to add the vectors graphically first and see what kind of estimate you're going to get for your adding by components. And you resolve vector into those components like we did here or there. 90% of the time you're probably going to do this rather than the triangular method anyways. If this works better for you, go ahead, use the triangle rather than the parallelogram. But you got to see that it is exactly the same approach with the parallelogram. Remember, parallelogram sides are parallel, opposite sides are parallel and equal to each other. So this is v sub x, this is v sub x. This is v sub y, this is v sub y. You have to calculate components using sine, cosine, or maybe tangent if you're looking for the vector itself. Add components in each direction. So you add all the x components, you add all the y components, you get some kind of a net quantity for each direction. And then go with the Pythagorean theorem, combine the total x components with total y components, square them first, then add them and do the radical out of it. And once again, that's only for the magnitude. Do not forget to define the last step, at least the tangent of angle. I really want the angle itself, but if arctangent, the inverse tangent function is a mystery for you, at least give me the tangent. But your calculator should be able to give you arctangent as well, just a press of a button. Google how to do the arctangent on your calculator, and you'll see the magic that comes with it. Instead of tangent of an angle, you'll be able to tell the angle by itself. So here is some practice. Which of the methods of combining components are correct? Well, you already see the answer because I don't want to do animations. Let's discuss all of them and see what's wrong with any of the options. Option A, what do we see? We see a sub x, which makes sense. It's totally possible to have a sub x. It's a negative value, but still along the x-axis in the opposite direction, perfectly fine. You see a sub y component along the y-axis. Yeah, its opposite direction is going to be negative, but so far so good. Totally valid way of adding vectors. And what do you see here? You see that there is an attempt to do the parallelogram method, but there is a mistake in this method because remember, for parallelogram method, you start everything from the same point. And the final vector sum comes from something else. It's not the original point where the two components start from. So what's incorrect for option A is the diagonal is incorrect. It's the wrong diagonal. Okay, for option B, same thing, a sub x, a sub y. And what do you see? Same mistake, it is the wrong diagonal. You can't pick this diagonal because all vectors start from the same point, a sub x, a sub y, and your vector A should be pointing this way, south of west. That would be the correct answer. And finally, option C is good. It's not a parallelogram method anymore. We see a nice triangle here. And we got a sub x plus a sub y tip to tail, tail to tip. And finally, we get the proper diagonal for a parallelogram, or the beginning of the first towards the end of the second vector. This is how you show the vector sum. Okay, same question, different setup. What do we see here? We see a sub y plus a sub x, right? Tip to tail. the beginning of the second, all the way to the end. And then the first one starts from the end and goes in a certain direction. So this is a triangular method. And you would say, hey, it's not a sub x plus a sub y, it's rather a sub y plus a sub x. And I say, fine, there is a commutative law that allows me to flip-flop the first and the second vectors. So a sub y plus a sub x, or a sub x plus a sub y, you still get the same result. What's wrong with option B? A sub x plus a sub y, everything's fine, but then see how the direction of the final vector is opposite to what it should be. You can't choose direction randomly just because you want it this way. You're going to get something different. So that's a mistake. The correct answer is still south of west. This direction is now north of east, which is incorrect. Magnitude-wise, it is the same. I have to say magnitude is correct. But for a vector, it's always two things, magnitude and direction. For option C, it's all good. Classic parallelogram method. Everything starts from the same point, x component, y component, and the answer for the vector sum starts from the same component, and you can see that it's exactly the same answer as for a triangular method with commutative law applied. Once again, any questions, please type them in the meeting chat, and we'll discuss them a little later. Okay, so this was direction. Do not forget that you have to keep track of the sign. Is it a positive component or a negative component? Let's take a look at two vectors, d1 and d2. The first question is, what's the sign of d1 sub x? X means x component. So if this is d1, then the x component is the projection of d1 onto x-axis. That's the direction. Do you see how you start from the same point and you go towards positive direction, right? Positive direction. That means that the sign of d sub 1x must be positive. How about d sub 2x? That's my d sub 2. And that's the initial position. That's the final position onto x-axis. Same thing. I do have component that is pointing towards the positive direction. And that was my choice to choose x to be this way, being positive. You can flip-flop things around, and yeah, then it's going to be negative. But until you do the flip-flop, d sub 2x is also positive. d sub 1y. So d sub 1, projection onto y-axis. This is the initial. This is the final. See how it is pointing upward. The component of d1 onto y-axis points upward. And that's my choice for positive y-axis, positive direction for y-axis, though it's got to be positive as well. And now we got d sub 2y. This is my d sub 2. And you can see how it's pointing kind of downward, right? This is my top value, say, I don't know, 10. And this value corresponds to something less than 10, say 5. And your component is final takeaway initial. Final is 5. Initial is 10. 5 minus 10. That's a negative 5. Doesn't matter the value. What matters is it's negative. So d sub 2 component onto y-axis is pointing downward, opposite to what we have chosen to be positive. So if it's opposite, then it's negative. Okay, so we got through the introduction / review of vector algebra. It's time to solve some physics. And the largest application that you can think about for kinematics in 2 dimension is what we call projectile motion. For a projectile, pretty much everything qualifies as a projectile once you have the gravity acting on it and it's the only force. And you might say, oh, we always have air resistance. Good point. But then you have to recall that our model for kinematics says what? No air resistance. You have to neglect the drag from the atmospheric air. And that's what exactly we need for solving projectile motion problems, because if there is no air resistance, the only force that changes the direction of motion and magnitude of velocity is gravity. Gravity creates free fall acceleration. Instead of just acceleration, we say g, small g. And what's even better, it is a constant. It's 9.8, pointing downward at all times. Don't you ever say acceleration is 0? There's no such thing for projectile motion. There's always gravity. Oh, by the way, don't you ever say there's no gravity in space? We're going to discuss the question on why are astronauts weightless in space, and you should never ever say, oh, because there is no gravity in space. It's a total misconception. The real reason is free fall. And if you want the proof for this statement, you should think the moon. You know that the moon orbits the Earth, right? What's the reason? The reason is gravity between the Earth and the moon. The Earth pulls on the moon, moon pulls on the Earth, and there is gravity. And the moon is like 400,000 kilometers away. So compare that to a space shuttle, which is just a few hundred miles away. There's definitely gravity. So there's always gravity in space. Gravity is the only reason for the moon to orbit the Earth to orbit the sun to orbit the center of the Milky Way galaxy. And the Milky Way galaxy by itself is a part of local group galaxy clusters. You got the idea, right? I don't have to go any further. That's everything because of gravity. So there's always gravity in space. And for all the problems for the surface of the Earth, you have constant value. So multiple pictures taken from a basketball shot. What do you see? You see that the trajectory for any projectile is always a upside down parabola. There's a vertex point. There's your initial. That's the final. And if it's the same level, you'll get a nice smooth parabola that describes the symmetry of such motion. So I'm pretty sure you've seen that before. There shouldn't be a confusion on what kind of projectile motion is that. Well, it's a parabola. Yeah, and what you see here is actually motion in 2 dimensions. You have X component, right? You throw the ball from here, and then X component changes, right? Once it hits the basket. And your vertical component changes as well. It was, say, 0. Now it goes to a certain altitude and then goes back up until the ball hits the ground. What's good about this 2-dimensional motion is that the time goes the same for both directions. If you want to solve the x component, whatever is the time you want to pick will match the time for the y component. Time runs the same way for both components, which is a very good hint to keep in mind. So motions are independent of each other. You have your x motion, and it has no connection to y motion until you really want to connect them and show that it is a parabola. And time is good for both dimensions. And that's going to be our helping hand for solve projectile motion. So instead of just horizontal and just vertical problems that we solved in chapter 2, we're now going to solve 2 problems simultaneously, 2 for the price of 1, if you will. Good news, equations are exactly the same. Remember the v sub 0 plus at and x sub 0 plus v sub 0 t plus at squared over 2. Well, it is going to be 1 for x, and then it's going to be the same setup for y-axis. And like I said, time is going to be the same for both components. So let's talk about projectile motion when you throw something horizontally. See, there is a initial velocity vector in that direction. It's horizontal. It's parallel to the x-axis. And I'm pretty sure you've seen what's going to happen to that projectile. It's going to fall as an upside down parabola. Why is that so? Because we have free fall acceleration that changes the velocity vector. So instead of just horizontal motion, you see you have vertical component of the velocity that grows with time. See, it was 0. Now it's like negative, I don't know, 10. Then it's negative 20, negative 30, negative 40, because of the free fall acceleration. Acceleration is the change in velocity, and that's exactly what you see here. You have initial velocity, and then you have the change that increases the vertical component. Or, if you want the easy case, ignore the horizontal component in the first place and just let it go, the free fall. What do you see? You see the projectile speeding up downward because there is a change in velocity. Every second, you increase your velocity by 9.8 units, meters per second to be more specific. Okay, remember the 2 tricks we discussed in chapter 2? Every time you reach the maximum altitude, you momentarily stop in terms of the vertical component. Let's take a look at the projectile motion, the general projectile motion. You start at a certain angle, and if you throw something from the desk that you're sitting at, say in the opposite corner, draw a pencil, draw a pen, you will see the projectile motion as a upside down parabola. And let's think closely about what we have at the topmost point for the velocity vector. I want to point out that because acceleration is strictly downward, it's vertical, there is no change to the horizontal component. See, it was, say, 5 units in the positive direction here. It's still 5 units in the same direction. It's still 5 units, and still 5 units, and it's still 5 units there. So no change in the x component whatsoever. But your vertical component definitely goes through a change. It had a huge positive component in the beginning, and then it gets less and less and less up until you hit the topmost point. And what's so special about it? At this point, we get 0 vertical component for the velocity. You momentarily stop. And if you don't believe me, grab a pencil, throw it upward, and see what's going to happen at the topmost point. For vertical component, For vertical motion, the pencil is going to stop at the topmost point, and then it's going to go back. So your vertical component becomes negative, and it grows, you're speeding up, because your acceleration has the same sign as the velocity. You will be speeding up on your way back to Earth. And this is the point that you're going to use to solve some problems on what's the greatest altitude, what's the highest altitude that you reach in that projectile motion. You say it's going to be the maximum when vertical component of the velocity is equal to 0. Horizontal component is still there. Don't you say velocity is 0. Velocity is never 0. The projectile keeps on going on and on and on. But the vertical component at this point is 0. And the second trick is shown here. Once you throw something in the air, it's going to go back. And once it hits the ground again, you are back to 0 position. Okay, it was 0 vertical component for velocity. Now, once you hit the ground, it's 0 vertical position. Your y is equal to 0 once you hit the ground. It's not given specifically, but this is your common sense that you have to use in order to set up a system of equations to solve those problems. So at this point, the vertical component for the position is 0. Is x 0? No way. X has changed like dramatically. But vertical component is once again 0. Let's take a closer look at the initial velocity vector. See, we have the so-called initial velocity and the reference angle for that vector. This vector can be decomposed into 2 components, the x component and the y component. And let's take a closer look. What do we see here? We see a parallelogram method heading to vectors, which you can also think as triangular method, v sub x, v sub y. And this is your hypotenuse for a right triangle. If this is your reference angle, then you can easily calculate the x component as adjacent side, and therefore you're going to use a cosine function. Or if you want the y component, see how this side of the parallelogram is equal and parallel to this side of a parallelogram. So sides are equal, therefore this side is the same as that side. Your y component is the same as the opposite side in this right triangle. Opposite means sine function. So if you have the angle or you want to solve for the angle for the initial velocity, you're definitely going to use this trigonometry trick for solving the components for the initial velocity. So let's practice. Let's actually solve one and see what's going on. So there is a projectile, doesn't really matter, it's just a particle. It can be a ball, can be a ballistic missile, can be, anything. And it's thrown at a certain angle with respect to horizontal. And this projectile is going to land back on the ground at some point because there is a free fall acceleration. And what we know about it, it's constant. It's pointing downward and it's constant. So if it's constant, we can use our set of 2 kinematics equations. And the first one is the velocity equation. Let's do it for the x-axis, for the x component. So my x component of the velocity at a certain moment of time, t, is proportional to the initial velocity x component, which is right here, plus the acceleration times the time. Now, listen carefully, closely, make a note, huge note for you to keep in mind for the rest of your physics experience. The note is, every time your vector is perpendicular onto a certain axis, the component of that vector onto that axis is 0. Okay, once again, every time your vector is perpendicular, means 90 degrees, with respect to a certain axis, the reference frame, if you will, reference axis, its component on that axis is equal to 0. This is exactly the case right here. See how my acceleration, which is g, is perpendicular to x-axis. And if it is the case, if you have vector perpendicular to a certain axis, then your acceleration on that axis is 0. Why is it 0? Easy to prove. Components are final takeaway initial. This is the final, and onto x, it's going to give you a certain value. Give me any value, whatever the value is, like say 50 units. And what's the initial value? The initial value projected onto x-axis is the same value. It was 50 here. Now it's 50 there. And component is the change. Final takeaway initial, 50 takeaway 50, 0. That's why the x component of the acceleration vector is 0 this time. So what do we get here? We get that no matter what the time is, you multiply by a 0, and that's just 0. So your x component for velocity vector is constant. It never changes. Whatever is the initial component, this v sub 0 cosine theta, it's going to stay as this value for the rest of the motion. No change for horizontal component of the velocity vector. Because there's a 0 change for velocity. Because the acceleration, which is the change, is perpendicular to that axis. Will acceleration be 0 onto y-axis? No. See how it's not perpendicular, they are anti-parallel? Well, the key word is parallel, right? If they're parallel, it's positive. It's anti-parallel, it's negative, but it's never 0. So there's definitely going to be acceleration onto y-axis. The y component of the velocity will change, but the x component stays constant. Yeah, so if you discuss the idea of the vector being perpendicular, final takeaway initial, final is whatever is the value here, initial, same value, you get. Oh yeah, I even have the detailed initial, final. See how onto x-axis, your final is 6, initial also has value of 6 takeaway 6, 0 units. But onto y-axis, what do you see? You were at 5, now you're at 1. 1 takeaway 5, you get a negative value. Doesn't matter 4 or whatever. The point is, if positive y direction is upward, then the opposite is downward, and it's going to be a negative value then. Oops. Negative value here. On to the second equation. Remember, we have 2 equations. The first one for velocity. Now it is position. Position, and to be more specific, my x, horizontal position. We already know that it depends on the initial position, initial velocity, and the acceleration. And we just proved that acceleration onto x-axis is 0. It has a 0 value because it's perpendicular to x-axis. So the last term becomes 0. It disappears from your equation. And you get initial position, which is most likely going to be 0. Not necessarily, but most likely going to be 0. Initial velocity times the cosine. Why is it the cosine? Because we're talking a component that is adjacent to a vector of interest with the reference angle. It's adjacent to it, so it is a cosine function for the x component. Times the time. So if you want to know the range that your projectile is going to travel, all you need is to figure out the time that it's going to take to get there and the initial velocity. And that's all you need to calculate the distance, the displacement for the x component of motion. For vertical motion, same equation, but now it's not the x components, it's y components. And what's different for y components? For y component, if this is theta sub 0, then alternate interior angle is right here, and those are congruent. So everything opposite to an angle becomes the sine function. So once again, this is theta, therefore this is theta, and you have a side that is opposite to theta now. An opposite function is the sine. So for vertical motion, it's v sub 0 times the sine of the angle, not cosine. And what do we say for acceleration? As before, it is negative 9.8, negative g. It's not 0 because it's not perpendicular anymore, right? It's perpendicular onto x-axis, but it's parallel to y-axis. To be more specific, it's anti-parallel. It's the opposite direction. That's why the value is negative. And for the position function, for the y-axis, chances are you're going to start from the ground, so this is going to be 0. Your initial velocity has now sine function, not cosine, as for the velocity equation. Time is time. Pick a moment of time. That's what going to be the t value here. And the acceleration is once again negative g, but there's 1/2 in front, and t goes squared. So this is your general equation for vertical part of the projectile motion. Yeah, there's no need to memorize which one is sine and which one is cosine because it really depends on the reference angle. If your reference angle is here, then yes, it's going to be cosine for x and sine for y. But your reference angle can easily be the other angle. And if you choose this one to be your reference angle, then you're going to get cosine for vertical and sine for horizontal. So it's not always cosine for x and sine for y. It's really like not even close to be the general case. It just turns out to be that way if you choose the same coordinate system as I did for the previous problem and proceed with this reference angle. But for systems that we're going to discuss next, you'll get all sorts of angles. So you really want to get a good grip on which one is a cosine, which one is a sine, and make no mistake there, because if you don't know your sine and cosine, unfortunately, I have to penalize you by a lot of points. That's prerequisite for this class. Trigonometry. I'll help you, of course. I'll show you examples. And if you lost, let me know. I'll definitely help you. Okay, we do have some more stuff to discuss in terms of lectures, but it's already an hour. So I'm going to pause the video. We're going to stop here. And then we'll discuss the second part of chapter 3 in the next video, which would be next week. Let me stop recording.